All right, let's look at examples of Lewis structures. So we've already looked at CH4. Let's just count valence electrons so you can go back and look at that structure and do it for yourself. CH4, carbon has 4 valence electrons plus 4 hydrogens, which each have 1 valence electron, will give you 8 valence electrons on that structure. Also go back and take a look at the NH3 structure that we drew earlier. Draw it for yourself. Nitrogen is going to start with 5 valence electrons plus 3 hydrogens, each with 1 valence electron, which again is going to give you 8 valence electrons. So go back, look at those structures, draw them for yourself using these number of valence electrons. Let's look at a molecule we haven't looked at yet. H2O. This is going to be somewhat similar to the ones we've looked at before. Watch this. So oxygen, our oxygen here, you look at your periodic table, that's going to come with 6 valence electrons. And as you can see, it's got 2 hydrogens attached, so 2 times 1. And I'm sure you've already calculated that it's 8 valence electrons. Now, since this is a new molecule compared to the others, let's do this. Oxygen is in the center. Attached is each hydrogen by 1 single bond. Now, we've started with 8 valence electrons. We've used 2, 4, because there's 2 single bonds. Each single bond contains 2 electrons, giving us remaining 4 valence electrons unused thus far. These become our lone pairs on the oxygen. So 1 lone pair and a second lone pair, and that is the structure of water. Now, let's move on to a slightly more challenging structure. SiF4, so silicon tetrafluoride, as you'll learn to pronounce this, but we will do that later. To begin with, number of valence electrons. Looking at your periodic table, you can see that silicon is beneath carbon, so that is 4 valence electrons there from silicon, plus, now we're adding to that 4 fluorines. Each fluorine, being in group 7, contains 7 valence electrons. 4 times 7 gives us 28, plus 4 is a nice 32 valence electrons that we need to keep track of. Okay, so just like carbon, silicon is going to go in the center. So silicon first, then we attach each fluorine by a single bond. Like so. We don't want a hydrogen. Let's make that a fluorine. Okay, so now we've gone 2, 4, 6, 8. So that is minus 2 times 4, or 8 electrons for those single bonds. 32, of course, minus 8 would give us a nice remaining 24 valence electrons. Okay. Now, let's begin putting these on the fluorines first. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. And there is our finished structure, because you can see we went minus 4 times an additional 6 electrons placed on those total fluorines, giving us a total of 0 unused valence electrons. And that is the final structure of our SiF4 molecule. Let's move forward and look at another one. Here, we're going to draw the structure of NCl3. So to begin with, number of valence electrons is going to be nitrogen contains 5 plus chlorine. That's going to be 3 times 7. 3 times 7, of course, 21 plus 5 gives us 26. Okay, so nitrogen in the center, forming single bonds to chlorine. That gives us minus 3 times 2, a remaining 20 valence electrons. So now we just start putting valence electrons on our chlorines. 2, 4, 6, 8, 10, 12, 14, 16, 18. So we've gone 3 times 6. Subtract that off because that's the ones we've used for the chlorines, giving us a remaining 2 valence electrons. We look at the nitrogen. The nitrogen has an incomplete octet. Those last 2 electrons go onto the nitrogen, minus 2, giving us 0 remaining valence electrons. And there is your NCl3 structure. As you practice these, see them more often, you'll be able to draw these much more rapidly. Okay, let's look at something with multiple bonds. So let's look at the molecule CO2. Number of valence electrons. Carbon has 4 plus 2 times 6, because oxygen, when you look at your periodic table, you'll see contains 6 each, giving us 2 times 6 is 12, plus 4 is 16. Now, from there, of course, we know carbon goes in the center, single bond to oxygen, single bond to oxygen. So that is minus 2 times 2, giving us a remaining 12 valence electrons. Let's just put those now first on our oxygen. 2, 4, 6, 8, 10, 12. Okay, so minus 12. All our valence electrons are now used up. But wait, the next step is to look at our carbon. Look at that carbon. Does this carbon have an octet? So you ask yourself, does this carbon have an octet? And the answer you can see is it's got 1, 2, 3, 4, or 2, 4 electrons shared with it total. So it's 2 times 2, which is 4, which is definitely not an octet. So how can we get an octet? Well, like we said earlier, you can take lone pairs and now start sharing them with something else. So lone pair here, share that there. So that means the carbon now will now be double bonded to each oxygen. And that remains, therefore, each oxygen still has 2 lone pairs instead of 3 lone pairs. If you look at before the structure, you had 3 lone pairs on each oxygen. You share 1 lone pair each with a carbon, and that gives you now 2 lone pairs on each oxygen, 4 electrons from each oxygen shared with the carbon total. So carbon's got 2 double bonds. It's got 2, 4, 6, 8, gives you a complete octet. And that structure is now satisfied and complete. Let's look at a polyatomic ion. How about we do the structure of, let's do the structure of NO3 minus, good old nitrate, okay? So nitrate has 5 electrons from nitrogen plus 3 times 6 from oxygen. Now it's got a negative charge, which means plus 1 electron for that negative charge, giving us 3 times 6 is 18, plus 6 is 24 valence electrons. So we know we start with nitrogen in the center, single bond to each oxygen. Now let's add electrons to the oxygens. 2, 4, 6, 8, 2, 4, 6, and 2, 4, 6. Now let's count our total number of valence electrons that we have used. We now subtract off first 3 times 2 for the single bonds to the nitrogen, giving us, of course, 18. Then we used up those 18 electrons forming our lone pairs, giving us 0 remaining electrons to be placed anywhere else. Looking at our central atom, you can see your central atom currently is not got an octet. So there's no octet there on nitrogen. So what do? Well, we pick one of these oxygens, pick one, just one, and have it form a double bond. So now you end up with nitrogen double bonded to the oxygen on the left. It's still got 2 lone pairs, single to the one downstairs, like so, and the one on the right, single bond, like so. Now the final thing for an ion is you put brackets around it to contain it, and you put the charge in the upper right-hand corner to indicate the charge on that polyatomic ion as a whole. Okay. Let's make a note too that it did not have to be the oxygen on the left. It could have been the oxygen down, or it could have been the oxygen to the right. Whichever oxygen you choose becomes that one, but there is no requirement for it to be one of the oxygens on one specific side. All right, we'll stop here, maybe do some more examples later.